Hi, we are Group 9 and we are going to discuss groundwater contamination for our project. Groundwater is fresh water that comes from rain or snow. It stays underground and it is used for drinking. Extraction of groundwater can happen through pumping of a well or rise to the surface as a spring. Many facilities of our land's water supply is groundwater. Groundwater contamination are wastes or chemicals released to the environment. This has the potential to pollute groundwater. Contaminants that are dissolved in the water will move with the water. This has the possibility to travel to wells and be used for drinking, and it can also be a hazard to our health. A continuous source of contamination will form an area of contaminated groundwater called a plume. In this case, we will look at a liquid type of contaminant known as dense non-aqueous phase liquids or DNAPL. DNAPLs sink to form pools, therefore becoming a long-term source for groundwater contamination. Setup of groundwater situations. Relating the strength of the DNAPL source mass to the source mass gives us this equation, where gamma is empirically determined. There are situations where if gamma is greater than 1, large but short-term reductions occur in the concentration of the plume and mass. The source negativity is not affected strongly in this case. In the case where gamma is less than 1, source longevity is reduced significantly and the short-term reductions are smaller in the plume and mass. But in both cases, early source remediation is more effective before contaminant mass will enter the plume. Significantly, delaying source remediation will not affect after the leading parts of the plume and require additional efforts on the plume itself. Given these equations, we form this following equation. And after some calculations, this is the final equation. We also add the decay term due to biotic and abiotic degradation, which is proportional to the mass. Then we have this equation. And lambda represents the decay rate constant. Now we form Bernoulli's equation. Solve differential equations considering 3 cases. Solve differential equations considering 3 cases. Case 1. Gamma is equals to 1 and lambda is a regular number. We use this MATLAB code. We get the following general solution to case 1. Case 2. Gamma is not equal to 1 and lambda is equals to 0. We use this MATLAB code. We get the following general solution to case 2. Case 3. Gamma is not equal to 1 and lambda is not equal to 0. We use this MATLAB code. We get the following general solution to case 3. It is said that when gamma is greater than or equal to 1, the source longevity will not be strongly affected. Choosing case 1 where gamma is equals to 1 and taking the limit as t goes to infinity, we get m of t is equals to the initial condition. This tells us that when gamma is equals to 1, the source will have an infinite lifetime because m of t will always be equal to initial condition. Now, let's assume the following. We have a contaminant mass of 1,620 kilograms and its initial concentration is 100 milligrams per liter. The cross-sectional area is 30 square meters and the Darcy groundwater velocity is 20 meters per year. Let us also assume that there are no abiotic or biotic degradation. Therefore, the decay rate constant lambda is equals to 0. Let us consider the following case where gamma is equals to 0.5 and we want to determine the concentration of the contaminant from 0 to Tf, where time is concentration of the contaminant is equals to 0. Since lambda is equals to 0 and gamma is equals to 0.5, this is case 2. Solving this differential equation using MATLAB code. This is the graph. It tells us that given the following parameters, the contaminants will be gone after approximately 54,000 years if no remediation is taken. Let us consider a second case where gamma is equals to 2 from more than 0 or less than 100 years. Gamma is greater than 1 and lambda is still equal to 0. Therefore, this is still case 2. It tells us that the concentration will decrease, but there will still be approximately 9.93 times 10 to negative 5 kilograms per liter of contaminant after 10 years. Effects of partial source remediation. Let us assume that a source remediation process reduces the initial amount of DNAPL mass by 90% on the same groundwater. This would mean that our mass is r, m is equals to 0.1 mO, and our concentration is now the equation. We would like to know the concentration of contaminants will behave as time progresses for both cases when gamma is equals to 0.5 and when gamma is equals to 2. Here is the code we need. And this is the resulting graph. It tells us that even if 90% of the source is remediated, the concentration of the contaminants will only be 0 after approximately 17,076 years. Considering case 2 where gamma is equals to 2, we use this code in MATLAB. And this is the graph we get. This tells us that after 90% of the mass is remediated, the concentration will be approximately 9.93 times 10 to the negative 7 power kilograms per liter after 100 years. What if partial source remediation was delayed? Let's say that a partial source remediation was delayed for 10 years. Let's look at both cases where gamma equals 0.5 and gamma equals 2. For gamma equals 0.5, we can look at the concentration from 0 to 100 years. Using MATLAB, we get this graph. Based on the graph, the concentration will significantly decrease at time equals 10. This is because of the source remediation. If we solve when the concentration will be 0, it will be around 17,733 years. For gamma equals 2, we can again look at the concentration from 0 to 100 years. Using the following MATLAB code, we get this graph. It's almost the same as the graph in case 1, but in this case, if we try to solve for the time when the concentration will equal to 0, we won't get an explicit as gamma is greater than 1, meaning the source has infinite lifetime and the concentration can never equal 0. Partial source remediation is effective based on the problems that we solve. The concentrations of the contaminants will significantly decrease, but in some cases, the concentration of the contaminants will never be equal to 0, and in some cases, leaving the contaminants as is will be 0 on their own.